Okay? Hopefully we'll finish 9-3 today. If not, we'll definitely finish it next time. All right, so here we go. Okay, is everyone paying attention back there in the back row? Here we go. How many 5-card hands have exactly 1 king and 3 queens? All right, this shouldn't be bad for us. How many 5-card hands have exactly, let's just one at a time, 1 king. How do you get 1 king? 4C1. Now do not look at me like you are confused by that. How many kings are in the deck? 4. How many do you want? 1. 4C1. There we go. Now let's take care of the queens. I need 3 queens. 4C3. Now what do I do with these 2 numbers? Multiply them. 1 king and 3 queens. Am I done? No, because it's a 5-card hand, and how many have you chosen so far? 4. There's 1 more card to get. And what about that 1 more card? It cannot be a king or a queen. So how many different cards are there in the deck that are not kings or queens? 52 minus 8, or 44. So there are 44 other cards, and you are going to choose one of them? That's it. Everybody got it? A class has 15 boys and 10 girls. 3 students are selected. What is the probability of having exactly 2 boys? Okay, now remember, probability is a fraction. This is kind of a new type problem for us, although the components you know how to handle. Forget that it's probability for a minute. What if I said, how many ways can I get exactly 2 boys? What would that look like? I want to get exactly 2 boys out of this group. 15C2 and 10C1. Why? You're choosing 3. And if 2 of them are boys, then the other one has to be a girl, right? So does that make sense to everybody? Now, this is a probability question. Every probability question ultimately is going to be some kind of a fraction or a decimal, right? What's the denominator? The denominator of a probability question is always the total ways things can happen. Think about that. Don't be confused. If you roll a die, what's the probability you'll get a 2? 1/6. Why is there a 6 in the bottom? Because there are 6 possible choices. So what goes in the bottom here is all the possible ways I can pick 3 people. How many are there? 25. C3. That's my denominator. Why 25? Because there's 25 total people. And why 3? Because I'm choosing 3 of them. Your denominator is always the total options you have. 25 total people, 3 total chosen. Okay? All right. Here's another probability. What is the probability of guessing exactly 4 correct on a 10-question multiple choice quiz if each question has 4 options? All right, this is a different probability than this one. It's a different kind of problem. We talked about number 3 yesterday, one like it. Anybody remember what our strategy is? What's going on? I am making 10 guesses. Guess 1, guess 2, guess 3. And I want to get 4 of them right. What's our strategy? This is a binomial probability problem. This is a Pascal triangle type problem. Okay? So I don't really want to build Pascal's triangle. I'm feeling a little lazy this morning. It takes a lot of space because I'd have to go to which row on this problem? The 10th row. And I don't want to go to the 10th row. So I'm gonna remember that if I were going to write out the 10th row, the first number would be 10C10, right? And then I'd have 10C9, 10C8, 10C7, 10C6, and so on. Now let's stop and think a minute. What does this number mean? It means there are 10 questions, and you're going to get all 10 of them, right? This means there are 10 questions, and you're going to get 9 of them right. Well, without writing them all out, which one do I want then? 10C4. Because I want 10 questions, getting 4 of them right. But in a binomial probability problem, there's more than just the coefficient. This is just some number. We'll type it in and get it on our calculator, but that's just some number. What else is there? What other components are there in a binomial probability problem? There's 2 more components, right? Binomial, and those 2 components are what? Right and wrong? And on this test, multiple choice 4 options, the probability of guessing correctly is 1/4. So you can either put 1/4 or you can put 0.25. It's the same thing. And then wrong would be 3/4 or 75%. Now there's one more piece to it though. You don't stop here. What's missing? The exponents. And the exponents will be what?
How many you want to get right?
How many you want to get right, which is 4. And how many that means you're obviously going to get wrong, that is 6. So we would multiply all that together. So we probably should practice that. You didn't have to do this yesterday because you didn't have a calculator. But next week when we have a test someday, you're going to have to be able to do this. Now I got 0.146, which would be 14.6%. You may answer either way. Let me know how you did that. Let me know if you got that. Everybody match that. I think I typed it in right, but I never know. Is that what you got? Anybody match that?
Yep.
Okay. All right, good. And while we're at it, anybody have a question about that? Let's go ahead and type this one in and make sure everybody can get that one typed in. This one I got 45.65%. That seems awfully high. I think I made a mistake.
That's what I got too.
Did you get that?
Yep.
Okay.
I got 0.7.
All right, anybody have a question about either one of these before I erase them and go on to the next one? All right. How many ways can a pitcher and a catcher be chosen from a team of 9 players? You have 9 players, right?
9C2.
Our choices are 9C2 and 9P2. 9P2. Why is it 9P2? Because they're different options. They're different options. If I said I were going to pick, I don't know, 2 generic outfielders, then it could be 9C2.
Yeah.
But since I'm picking a specific person to be a pitcher and a specific person to be a catcher, it's 9P2. Everybody all right with that? How many ways can 7 books be arranged on a shelf if 3 of the books are identical? 7 factorial is the beginning, but then we have to divide by 3 factorial. And we divide by 3 factorial because the books are identical, and that's how we do identical things. Speaking of, look at the next problem. How many ways can we arrange the letters of this word? We start with 9 factorial because there are 9 letters.
Then they're 2 minus, so 2.
And then we go through, and just find anything we've got 2 of. There are 2 I's. Is that it? Alright, so that would be the answer. 9 factorial over 2 factorial. Everybody okay? There are 300 seniors at Cathedral. Oh, I'm just drawing a Venn diagram because as you do more of these, you kind of get a feeling for what strategy to use. And I've got 300 seniors, 240 take pre-cal, some love vectors, 90 love matrices, 70 say they love both. How many pre-cal students should we say they love neither vectors nor matrices? All right, so here we go. This box contains the 240 kids that take pre-cal or have taken pre-cal. Now I know there are 300 kids in the entire school, but that doesn't matter. We're only talking about those that have taken pre-cal because in that group, some of them like vectors and some of them like matrices. Exactly half say they love vectors. So that means 120 kids love vectors. Would you agree with me? But I am not going to put 120 right here. Does everybody understand why? Because some are in the middle. Do we know how many are in the middle?
No.
70 are in the middle. So if 70 kids love both, and 120 total love vectors, how many are here? 50. And then 90 love matrices. So there are 20 here. How many pre-cal students love neither one? All right, now wait a minute. How many people are inside these 2 circles? 140, right? So I got all 240 of you out here. I say raise your hand if you love vectors. All these hands went up. Raise your hand if you love matrices. All these hands went up. How many people never raised their hand then? 120, wouldn't it? Aren't there 240 altogether?
Yeah,
Oh wait, that's 140. Yeah, 100. Yep, 100. You're right. So there are 100 kids that don't like either one. The 300 is thrown in there to mess you up. It really doesn't have anything to do with the problem. Can you see that now that we've talked about it? How many ways can I award 3 identical prizes to my class of 39 students?
39 P.
39 C3. Why is it C3? They're identical. They're identical. All right, turn it over. This page, this one has a backside. Wow. This was a big one. Now, number 9 is a new problem for us. Now, if you worked ahead in your homework and maybe looked at some of the examples, you probably know how to do this. But number 9 is different. There's a 65% chance that Grant will come to pre-cal class on any given day. Grant had an attendance issue. If he comes to class, there's a 74% chance that he will pass the quiz. If he doesn't come to class, there's a 12% chance he will pass the quiz. Find the probability that Grant will not pass the quiz. Okay. sounds different, right? I mean, this problem is different than the other ones we've done. Here's what I'd like you to think about. There are two things happening in this problem. The first thing that has to happen is Grant has to come to class or not. That's the first thing that has to happen. What's the probability that he will come to class?
65%.
0.65. So the probability that he won't come to class is 35.35. All right, so now that decision's made. He's either come to class or he's not come to class. So now what's the next layer of the problem?
Whether he'll pass.
He either is going to pass the quiz or not pass, right? Now, if he comes to class, we are in the come to class branch right here. If he comes to class, what's the probability he will pass? 74. So the probability then that he won't pass is 26. Now what if he doesn't come to class? Now we're on this branch. He's decided not to come to class. So what's the probability he'll pass the quiz? 12. The probability he won't pass is 88. So this problem is done in layers or levels. What does this branch right here represent? This branch right here, what's happening on this branch? He's coming to class and passing the quiz. So this branch, I need a total probability for this branch. He's coming to class and passing the quiz. So what am I going to do with those two numbers? Multiply. It's an and. So 0.65 times 0.74, 0.481. So 0.481 is the probability that he will come to class and pass the quiz. Now, what's this branch right here? Come to class and not pass the quiz. So that's 0.65 times 0.26, 0.169. What's this branch? No coming to class, but still passing the quiz. Oh, 0.042. Take heed, it's better to be in class. What's this one? No class and no pass. Now, before we answer the question, I want you to take everybody understands where these four numbers came from, right? And what they represent. Would you add them up for me? Add them up. What did you say, DeAndre?
It should equal 1.
Of course it should equal 1. Because there's nothing else that can happen, right? This is everything. So these are going to add up to 1. Now, what's the question?
What percent?
Find the probability that Grant will not pass.
You just take the 2%.
Not pass happens here, right? And not pass happens here. So there are two ways he can not pass. He can come to class and not pass, or he cannot come to class and not pass. What am I going to do with these two numbers? Add them together. Because it's this branch or it's this branch. So 0.477 is the answer to the question. Is that right? Now we'll do a couple more of those. There's some in your book. We'll pull them out. This is not a binomial probability problem. This isn't like guessing on a multiple choice test or hitting a target or missing a target. This isn't that. You're not doing this over and over and over again. This problem has layers of probabilities. Coming to class, passing the quiz. We'll practice some more. You'll get better at it. How many ways can 4 boys and 3 girls be seated in a row? 7 factorial. Do not be bogged down by the fact that these people are some of them boys and some of them girls. That doesn't have anything to do with it, right? We have 7 people, we're seating them in a row. Nobody has to be together, nobody has to be apart. We're just seating them in a row. How many ways can you arrange 15 students around the tree? 14 factorial. Why? Because it's 1 less in a circle. Chloe?
So on number 10, why is it plus and not multiply? When do you multiply the two numbers? Number 10, you don't multiply or add anything. I know, but when do you multiply? When would it?
You multiply when you're doing 2 things together.
Okay.
How many ways can you set 3 algebra students and 6 pre-cal students in a row if the algebra students must be seated together? 7 factorial, 3 factorial. Now, why is it 7 factorial?
Because the algebra students
If
become 1.
3 count as 1, and you got the other 6?
Yep.
And then the 3 factorial is the group, right? Got it? All right, let's open up our books now. Do some other random probability problems. So we're on page 728. I'm sure some of these were assigned. I'm just going to do a couple of problems of various sorts of probabilities. So the first one I'm going to do, I'm on page 728, section 9.3, 728. The first one I'm going to do is literally problem 1. 9.3, and I'm going to do problem number 1. A red die and a green die have been rolled. What is the probability that the sum is 9? So I have rolled a red die and a green die. And I want to know what the probability is. Probability is a fraction. There's my fraction bar. I need a number on top and a number on the bottom. And I want the sum to be 9. All right? Let's create what's called a sample space. How do you roll 2 die and get a 9? What could happen? The red one could show a 6, and then the green one would have to show a 3. Or it could be vice versa, right? We could get 3 on the red and 6 on the green. All right, is that it? Are there any other? We could get a 4 and a 5, or a 5 and a 4. Is there anything else? Any other way to get a 9 on 2 die? That's it, right? So my numerator is 4. Why is my numerator 4?
There's 4 ways.
There's 4 ways. Remember, the top is what you want. There's 4 ways I can get a 9. Now, what goes on the bottom? The total number of ways that you can roll 2 dice. Now, could we continue this and write out all the possible options? Absolutely you could. That would take a while, but it would work. You can also just kind of think about it for a minute. When I throw this red one, how many ways could it land? 6. Then I throw the green one. How many ways could it land? 6. So red and green could land how many ways? 36 ways. So your denominator is 36. There are 36 ways 2 dice can land. The first one can land 6 ways, and the second one can land 6 ways. So if you wrote out, like these combinations, if you wrote all of them out, there would be 36 of them. Okay?
Wait, where did you get 36?
6 times 6. The first dice can land 6 ways. And the second one can land 6 ways. It's like building a license plate. How many options for the first dice? 6. How many options for the second one? 6. So both of them would be 6 times 6, or 36. Number 3. The number on the red is greater than the number on the green. Alright, so let's look at that. The number on the red is greater than the number on the green. So, could the red one show a 1? No. Could the red one show a 2?
Yes.
But if the red one showed a 2, the green one would have to show a 1, right? Could the red one show a 3? Yep. And then the green one would have to show a 2 or a 1. Right? So I'm going through and I'm trying to figure out all the options where red's bigger than green. So if red were 4, I could have a 3, 2, or 1 on green. If red were 5, I could have a 4, 3, 2, 1 on green. And if red happened to be 6, I could have 5, 4, 3, 2, 1 on green. Would you agree with that? How many is that? I got 15. I think there's 15. Yeah, there's 15. So the numerator of my probability problem is 15. What's the denominator of my probability problem? 36. Anytime you roll 2 dice, isn't your denominator going to be 36? 6 times 6, 6 options times 6 options. So that reduces to something, I'm sure. 5/12, so your probability is 5/12. Now, what was my strategy on these problems? We're talking about different strategies for probability problems. My strategy here was simply to count up the options. I wrote them out. I just wrote them out and counted them up. Will that method always work? It absolutely will. What's the drawback of it?
It might get bigger.
Depending on the problem, it can get really big, but it will always be an option. Okay? It will always be an option. All right, the next one I want to do is number 17. Now, you have to look up a little higher here to get all the stuff to do the problem. It says a peanut version of the same candy. These are like M&Ms. So we got peanut M&Ms, and then they have all the same colors except tan. Okay. The proportions of the peanut version are given in the following table. So what that means is that little chart there above problem 17, that little chart says that if you have a brand new bag of peanut M&Ms and you reach in and pull one out, the probability it will be brown is 0.3. And if you reach in and pull one out, the probability it will be red is 0.2. Get it? They've just given you the probabilities of each color. So number 17 says, suppose I have 2 bags, right? And Katie reaches in and grabs one, and Zach reaches in and grabs one. What's the probability they'll both get a brown one? So we want brown and brown. What's the probability the first one will be brown? 0.3. Now, before you say, I didn't know that, kids, it's in the chart. The chart tells you. The probability of getting a brown is 0.3. Alright, so Katie's probability in her bag is 0.3. What's Zach's probability in his bag? 0.3. Both of them are going to do this, so it's brown and brown. What am I going to do with those two numbers? Multiply them. So the answer is 9%. There's a 9% chance that that would happen. All right, number 18. Both are orange. Both are orange. Well, I want orange and orange. What's the probability of an orange? 0.1 and 0.1. So that's a 1% chance that you will get both orange.
1%.
One is red and the other is green. So I want red and green. All right, so here's the deal. They each have their bag. What's the probability Katie reaches in and gets a red one? 0.2. Then Zach has to reach in and get a green one, and it is also 0.2. So that probability would be 4%, 0.04. That is not the answer to the question. Why? The problem says, what's the probability of getting one red and the other green? Does it say Katie has to get the red one and Zach has to get the green one? No. So we have Katie getting red and Zach getting green, or we have still red and green, but Zach gets the red and Katie gets the green? What would that probability look like? Wouldn't it be the same thing? So what's the answer to the problem? 8%, 0.08, 0.08. Olivia? I know you're tired. I know theater's going long. Apparently baseball's going long. I'm sure everything's going long. But we have a job to do. That requires you to be thinking. Does everybody understand the or in there? It says one of each color. So I could get red and green, or I could get red and green. The first one is brown and the second one is yellow. Is there going to be any or in this problem? No. First one's brown, second one's yellow. That's going to be 0.3 times 0.2. How about neither is yellow? Neither is yellow. So I want not yellow and not yellow. That's what I want. Not yellow and not yellow. What's the probability of not yellow? 0.8. And not yellow, so the answer is 0.64? DeAndre?
0.64.
The first is not red. The first is not red. What's that probability? 0.8. And the second is not orange. 0.9. The answer is 0.72. So, right now, so far, a couple different strategies we've talked about is, first example with the with the dice, we talked about sometimes it's just easier to write out the sample spaces. Just write out your options. Here we had a chart or a table of probabilities, and so we used the chart of the individual probabilities to help us answer the questions. All right, let's see what we have next. Look at number 27, O-Venn diagram probability. All right, so let's look at number 27. So I have a Venn diagram, and I've got two things happening, A and B. And this notation, I can't remember if we talked about it or not, but this notation means the probability of A. So the A circle is 0.6. The B circle is 0.5. And the probability of A and B, and I'm going to use the official notation, the probability of A and B is 0.3. So help me fill in my Venn diagram. The whole A circle is 0.6. The whole B circle is 0.5. What's that? That's right here. Now, if the whole A circle is 0.6, then this has to be another 0.3. And if the whole B circle is 0.5, that has to be a 0.2. Now, wait a minute. This is a probability problem. What did DeAndre tell us a minute ago that was really, I mean, it's so fundamental. Probabilities have to add up to 1. So what do I have represented so far? There's only 0.8 up there, right? What does that mean? 0.2 is neither A nor B. So now we can answer the questions. Draw a Venn diagram, we got it. Find the probability that A occurs, but B does not.
0.3.
Now, using the official notation that we talked about the first day of this unit, the probability that A occurs and B does not would be this. That's A and not B. Does everybody understand that in terms of the notation that we used before? So what's that probability? A and not B? 0.3. It's you're in the A ball, but you're not in the B ball. B occurs, but A does not. That would be B and not A. So you're in the B ball, but you're not in the A ball, so that would be 0.2. I'll find the probability that neither A nor B occurs. So that would be not A and not B. You calculated that when you built your diagram. That's these guys, right? Are the events A and B independent? That is, does P, the probability of A given B, equal the probability of A? We are not going to talk about independent events, so you can cross that off. We're going to skip that, so you don't have to do that. So you do not have to do E. Now, would you and your neighbor try 28? It is the same exact thing, number 28. And again, you may skip E. All right, you may skip E. Would you try that one for me, real quick? Draw your Venn diagram. Miss Carlton, what are you working on there?
Oh, she wanted the.
Oh, thank you, that's fine. I thought you were comparing notes or something else.
Just freak out.
All right, Maria Carlson, Miss Chatty Cathy, you got your Venn diagram drawn?
No, I don't have my book, so I was gonna.
Okay. And so is that what's going on in this entire row? You have no books. And so our solution is to sit back and do nothing, right? Now, is that the best solution you can come up with? No. So let's kind of problem solve here. Maybe turn around, Wyatt's got a book, maybe take a picture of it. What a great idea! Wyatt to the rescue. Did we ever think we'd say that? Listen, people, if you are not prepared for class, you need to figure it out. Don't just sit there and do nothing, mister.
It is good.
Baseball players, I understand completely you're tired. Get your heads up. Not appropriate. Heads up. Heads up. I get it. Your head still has to be up. Yes. Actually, what you guys don't understand is, right now, you know, there are all kinds of buzzwords in education. Right now, a big buzzword is engagement. Okay, that means you're like paying attention to me. Okay, so when an administrator walks by, if your head is down on your desk, I get points. So I don't want to get points off. You get points off? Well, I don't even know how they're doing it, but it's a bad mark. Yeah, you get your mark down. I'm not sure it's points, but it's a bad thing. It's a really bad thing if the kid's asleep. It's a really bad thing if a kid is working on government or something in my class. So, you know, gotta kind of help me out here. I know you're tired, I get it completely, but you gotta pretend you care. All right, so here we go. Your Venn diagram has an A ball and a B ball. The probability of A and B is 0.2, which means that this was a 0.5 and this was a 0.2. Is that right? Did I do that? That automatically means this is a 0.1, because in a probability problem, everything adds up to 100% or 1. So now we can answer these questions. Were they the same questions, I think? Yeah. So the probability of A and not B, 0.5. The probability of B and not A, 0.2. And the probability of neither. Okay? So another strategy we have of doing probabilities is Venn diagrams. You'll get the hang, you'll recognize Venn diagrams as you practice more. There are situations where you've got these overlapping quantities. Some kids like social studies, some kids like math, some kids like both. That's a Venn diagram type situation. So you can use Venn diagrams to do probability. All right, let's take a look at 29. Now, to tell you in the directions, it will help to draw a tree diagram. We have only done one tree diagram problem, and that was the one where he came to class and passed the quiz. That's called a tree diagram. What did I tell you? How do you kind of know when you're going to use that strategy? Your problem is in layers. In what happens in the second layer depends on what happens in the first layer. Come to class or not determines your probabilities of passing the quiz or not. Well, read number 29. If it rains tomorrow, the probability is 0.8 that John will do piano. If it doesn't rain, there's only a 4% chance, or a 40% chance that John will do piano. So do you see how whether it rains or not determines the next level, which is whether he practices piano or not? That kind of relationship, it's called conditional probability. One thing depends on the other thing, is typically done with a tree diagram. That's a good strategy to use. So, what's the first thing? What's going to determine everything? What's going to be the first level of the tree? Rain or not rain? Absolutely. It's going to rain or not rain. Now, does the problem tell us the probability of rain? Yeah. It's 60%. The probability of rain is 60%, which means the probability of not rain is 40%. So tomorrow it's going to rain or it's not going to rain. Now, if it rains, this kid's gonna either do piano or he's not gonna do piano. Now, if it rains, what's the probability he'll do piano? If it rains, that probability is 0.8. So the probability of him not doing it is 0.2. What if it doesn't rain? He's still either going to do piano or not, but the probabilities are different. So what's the probability there? 0.4 that he will practice, 0.6 then that he won't. Does everybody understand that setup? So now we're going to answer the question. What is the probability that John will practice? Will practice. You don't need every branch up here. Which branches do we need? We need the ones where he's going to practice, right? So that would be that one. Or this one, right? It's going to rain and he's going to practice piano. What's the probability that it will rain and he will practice? 0.48. What's the probability that it won't rain and he will practice? 0.16. So what is the probability altogether that he will practice? 0.64. Why do we add those together? Because he's going to practice if it rains or if it doesn't rain. So the total practice probability is 0.64. You think you got a handle on that?
Yes, ma'am.
All right, let me see. I got one more here. How about number 40? Anybody have an idea about number 40? Those of you with no book, you need to be finding the book so that you can read question 40. It's going to be what? What's your thought, Millie?
20 CDA. That was mine.
Okay. Let's talk about that, Millie. What's the second part of that, or is that it? I mean, that wouldn't be it because it's a probability question. What's your?
Then there's 20 C14.
Would it also be like with the parentheses and then add on something?
So Millie is saying she's thinking this is a binomial probability problem. She's thinking there's a three-part, well, the first question is all 8 questions correct, so we'll do that one first. She's thinking this is binomial probability. Now, here's the deal. She's right. It's binomial probability because what's this kid going to do? This kid's going to answer 8 questions. And what's going to happen every time he answers 8 questions? He's going to get them right or he's going to get them wrong. Right? Right? Okay. So here's what's his probability of getting a question right?
14 out of 20.
14 out of 20. So the probability of getting the question correct is 4. This is correct. This will be incorrect. 14 out of 20 is his probability of getting the question correct. You go in, this kid goes into this test and he knows 14 answers. There are 20 possible. So randomly speaking, we got a 14 out of 20 chance of getting them right. Right? What's our probability of getting it wrong?
6 out of 10.
6 out of 20. How many am I going to get right? 8. How many am I going to get wrong in this problem? We're doing this first part. 0, 0, 0, 0. Kids, is he being asked 20 questions?
No, just 8.
Is he being asked 14 questions?
No.
He is being asked how many questions? 8. So he is going to guess, or answer, 8 times. And of those 8, how many does he want to get right? All 8. So his coefficient is 8C8. Now, you don't want to get bogged down in all the numbers in the problem. They all have a purpose. But in terms of this coefficient, it's all about, there's 8 questions on the test, and I want to get all 8 of them right. All the other numbers are incorporated in the probabilities. So what about the one that says exactly 5 questions correct? 5 correct. All right, now you said 8C5, and you are right, because you recognize that in Pascal's triangle, 8C8 means 8 questions, 8 right, 8 questions, 7 right, and so on down the line. You want 8 questions, 5 right. What's the probability of getting one right? 14 out of 20. I'm going to go ahead and reduce that to 7/10 because I'm going to type this one into my calculator. And I'm going to use 0.7. And then the probability of getting it wrong is 3/10. And I want 5 of these and 3 of these because there's 8 questions altogether. So let's type that in, see what we get. We'll type this one in right here, 8C5. I got about 0.254, or about 25.4%. Okay? All right. All kinds of probability today. We'll practice some more, but right now I'm going to give you a few minutes to go ahead and work a little bit on your homework.